Okay, so here we're going to swing back and revisit chi-squared distributions for the first time in year 13. We used chi-squared for a couple of different reasons. We used it for a contingency table to check whether or not there was independence between two different characteristics in the data, and we also used it probably more prominently for a goodness of fit test. We used it to try and test whether or not the observed data followed what we might reasonably expect from a particular distribution. So just a quick reminder of the formula that we used to calculate the test statistic. It's the difference between the observed and the expected squared all over the expected. And there's also an alternate version of this formula which some people do find easier to work with. I'm a fan of the original, but whichever one works for you, go ahead and use. They would both generate exactly the same answer, and you can see here a proof that takes you from the original through to this alternate version. Chi-squared was always used to try and test or to try and demonstrate the difference between what was observed and what was expected, and just how large that was. If the difference between what we observed and what we expected was a small value, then that's not too suspicious, that's not too significant. We know there's some variability within the distribution we're working with. But when we get a chi-squared score that is actually quite large, it shows that the observed values tended to be quite far away from what we expected. And if they're too far away, then they probably don't fit the distribution we assumed to begin with. Okay, so we're going to try and use this with some of the new distributions we've seen, and we'll focus on the geometric distribution here. So looking at this first example, Sarah has a large DVD collection, and she actually has a very strange way of picking what DVD she wants to watch. Every week, she picks a DVD off the shelf at random, and then she decides whether or not she likes to watch it. So she thinks there's about a 50% chance that she'll be in the mood to watch any particular DVD. Over the course of a year, she records the number of DVDs she picks before she picks the one that she wants to watch. So she's just recording how many she needs to go through before she picks one that she wants to watch. The results she records in the frequency table as seen below. We're told, but we should have been able to figure out, that this is a geometric distribution. Once she'd found a DVD that she wanted to watch, she wouldn't continue to pick DVDs. So as soon as she got a success, it was over. We've been asked to calculate the expected frequencies for each of these outcomes. So let's start with actually stating the distribution. So x follows the geometric distribution with a parameter of 0.5. The p is 0.5. So I'm just going to fill in this table. What is the probability based on the geometric distribution that there's one trial before we see our success? So the probability that x equals 1, 0.5. Similarly, the probability that x equals 2, well, the first would be a failure and the second would be the success. Even though they're the same value, I'll still lay them out like this. For x equals 3, we're going to need 2 failures followed by a success. So each of these probabilities can be added to a table, which you see that I've done above. Okay, so what's left to do? Just be really careful here. The probability that x equals 4 is 3 failures and then a success. So 0.0625. Now, let me just write these probabilities out and see if you can spot what the issue is. We know that all of the probabilities should add to 1. And at the moment, with the values we have here, they're not going to add to 1. Because our geometric distribution is infinite. It goes on forever. So me just stopping at 4, I haven't included 5, 6, 7, 8, 10, 100, 200. I've only included 4. So for this last probability statement, it needs to be exhaustive. I need to go for greater than or equal to 4. I need to group the largest value I knew was included with anything that might possibly exist above it. Okay, so we can easily do a 1 minus on the values that we do have, just to make sure that it does equal 1. So that all the probabilities do add up to 1. Okay, so now that I have those probabilities, we want to go ahead and find the expectations. Remember that the expectation is the probability scaled or multiplied by the number of trials. So The expectation of 1, well, there was a 50% chance that I chose a DVD I wanted to watch on my first go. So 1 multiplied by 52 equals 26. The expectation for 2 is going to be 0.25 multiplied by 52. And so on and so forth. So the expectation for 3, 0.125 scaled by n, 6.5. And the expectation for 4 or greater, it was the same probability, so I actually know it's going to be the same expectation. 0.125 multiplied by 52. Okay, just a quick check. Each of those do add up to give a sum of 52. Exactly what I was expecting. Well, now that we've calculated our expectations, and we already had observed values to begin with, I hope you can anticipate that we're going to be asked to perform a hypothesis test. We are being asked to do this in a roundabout way, in a different order to what we might expect, but we'll just go ahead with it anyway. The null hypothesis will always be that this distribution is a suitable model, or you can refer to it as a good fit. Because we were given the parameter in the question, we were told the value of p, we didn't estimate it, we would specify that within the hypothesis. Just be really clear on this, that I've actually written the distribution. X follows a geometric with a p-value of 0.5. For the alternate hypothesis, we can state that X follows a geometric distribution of 0.5 is not a suitable model. Or once again, we can say it is not a good fit. Either of these phrases will be fine according to the exam board and the mark schemes. You get to choose which one you would like to use. Just be consistent in your choice there. So in part C, we've been asked to check whether or not Sarah's right in her assumption, and we've been told to test at the 5% significance level. So still we weren't explicitly told to perform a hypothesis test, but we know that that's where we're going. So we're going to use the chi-squared test statistic as we usually would, and this is going to be the difference between the observed and the expected, squared, and then divided by the expected. So just putting those values in straight from the table. 33 minus 26 squared over 26, 12 minus 13 squared over 13, 5 minus 6.5 squared over 6.5, and finally 2 minus 6.5 squared over 6.5. So I always like to write this out. There are marks for this in the exam, rather than trying to do it just into your calculator, whether or not your calculator has a specific functionality to get you this value all at once. You definitely want to show the examiner all of these steps. Plus, I've noticed that the examiners are actually asking specifically in the question for you to show all of your work. So they anticipate you might try to do it just through the calculator and you may well lose some marks. This gives us an answer of 5.4231. Okay, so next we want to find that chi-squared critical value, so we know the boundary for a significant result to this hypothesis test. So let me just quickly graph a generic chi-squared function. We're using a 5% significance level, so we want to find out what is this critical value, what's this boundary value that lets us know whether or not we can accept or reject. We're going to be looking up our chi-squared score in the tables. We have 3 degrees of freedom. There were 4 observed values, so there's 3 degrees of freedom. Remembering that we would have also reduced the degrees of freedom if we had to estimate any of the parameters, which we didn't in this case. Okay, so looking up in the tables, the chi-squared score, which is exceeded by 5% when there are 3 degrees of freedom, is 7.815. From there, we want to make a comparison, and our test statistic is smaller than the chi-squared value, so we do not have a significant result. If it's not significant, then it could have just happened by chance, and we do not have enough evidence to reject H0. That's our mathematical conclusion. You already know that we also need to pair this with a contextual conclusion, and so we can say that there's evidence that X follows a geometric distribution of 0.5 is actually a suitable model for Sarah's DVD situation. So hopefully these steps are very familiar to you. It's exactly the same concept as any goodness of fit tests that we do, particularly those that we did in year 12, so the binomial, the Poisson, and all the other ones that we did. The only difference here is that we're looking at a different distribution. So we're swapping out how we found our probabilities, but everything else around it should very much be familiar to you. Okay, so just a couple of pointers for other types of questions that you might come across. So if you do have to estimate P, that's simply going to be the total number of successes divided by the total number of trials. Okay, be really careful here. You might take 3 trials to get 1 success. You might take 5 trials to get 1 success. So make sure you're calculating successes and trials individually and in a sensible way. Okay, so I'll just leave you with this rundown of exactly what we should be doing for the chi-squared goodness of fit tests. And this is for all of the tests. We'll start off by determining which distribution we're going to be working with. We set our significance level. We estimate the parameters if we need to. And that obviously plays in later on when we're deciding on the degrees of freedom. You write out your hypothesis, H0 and H1. Now this must be in words, and it must be the phrases that we've looked at. It's either it is a suitable model or you refer to it as being a good fit. After that, you can go ahead and calculate expected frequencies. Observeds are usually given to you as part of the question. Look out for where you might need to combine frequencies. Any expected frequencies that are less than 5, we're going to combine them together. You're going to go ahead and decide on the degrees of freedom. Once you have your degrees of freedom and your significance level, you can find the critical value from the chi-squared tables. After that, calculate your test statistic, make a comparison, check whether you have a significant result, and then you get down to your conclusions. It seems like a lot when it's written out, but these steps we've been doing and we've got very much used to. Just make sure that you don't leave any of them out.